Welcome to the 7th lecture of Module 5. Today's lecture will be focused on wire beam based additive manufacturing system where particularly a laser beam is used as an energy source. This is going to be the content for today's lecture. We shall start with the classification of the wire beam based additive manufacturing system when laser is used as an energy source. Then we shall discuss about the manipulators popularly used to handle such wire feeding based cladding units like the robot based systems and the CNC based systems. Then we shall discuss about the laser wire cladding unit particularly and the two most popular type of system where the wire is typically fed from the lateral side or the wire is fed omnidirectionally into the molten pool. Also, we shall discuss about the process parameters for this system. Then we shall discuss about the wire deposition characteristics, and in the end a little bit we shall discuss about the critical power which is required for depositing the material on a substrate or pre-built layer. So like in the case of electron beam, here also we are not considering the non-metals for the material in the form of wire, but only metals are going to be considered. The material will be transferred onto the substrate in a continuous form. However, drop-on demand may be explored but not very popular right now in the commercial systems. Then the machine kinematics could be serial kinematics, it could be parallel kinematics, or it could be the hybrid kinematics. Then the energy source particularly will be focused today on the laser-based systems. Then the mechanism for generating the support could be either by utilizing the multi-axis kinematics or no support system. We have already discussed that it is very difficult to provide some additional support in the case of metal when it is used as a raw material. Let us first discuss about the manipulator. Particularly when the laser arm is used, then a laser metal wire additive manufacturing system looks something like this as you are seeing on the screen right now. It used to be consisted of three major units, one corresponding to the laser unit from where the laser beam is generated and travels towards the laser cladding unit, which is here attached with the robotic arm. And then a wire is fed into the molten pool which is created by this laser, and then the third important unit here is the wire feeding unit. The laser unit is typically consisted of a power source where the laser is generated into the cavity and then travels. Typically nowadays a fiber is used in which the laser beam can travel towards the substrate. Also in the laser unit there is a chiller typically used to keep the temperature normal of the cavity where the lasing is happening. As you can see on the laser cladding unit side, the head is attached, the laser head is attached on a robotic arm which provides a relative motion between the substrate and the spot or the focal point of the laser beam. This laser beam creates a molten pool, and in that molten pool a wire feeder feeds the wire. To protect the molten pool from the outside gases such as oxygen and other gases, a shield gas is usually provided. As you are seeing here, the argon is provided and it protects the molten pool from the atmospheric gases such as oxygen. The relative motion between the welding head and the substrate is provided like by already mentioned utilizing a robot, and a controller is used to define the appropriate motion. The next possibility is if the CNC machine is used to provide the relative motion between the laser head and the substrate. In such case, as you see, the other systems are same like laser unit, there is a wire feeder and there is a a shielding gas unit which provides the shielding environment around the mold pool. The only difference here is that the robotic arm is replaced by now a CNC machine tool. Usually, these CNC machine tools are dedicated only for laser cladding system, or very popularly also retrofitted on the existing CNC machines. When the laser cladding has it retrofitted on an existing CNC machine, the CNC machine is capable of doing the machining operation as well as it is capable of doing the deposition operation. What you are seeing here right now is not a hybrid system. It is having only one possibility, as there is no machining unit attached here. The laser optical head is attached and it is fixed on a column, while the substrate is having X, Y and Z motion. It can be in a different way as well, in which the X, Y, Z motion will be there with the laser optical head and the substrate will be stationary. Or one axis will be with the laser optical head, or two axes will be with the substrate, or two axes with the laser optical head and one axis with the substrate. So these possibilities could be for the different CNC configuration, but the fundamental remains same. Now let us discuss in detail about the laser wire cladding unit. There are two possibilities for laser wire cladding unit. It could be either a lateral wire feeding unit or it could be an omnidirectional unit. When we say it is a lateral wire feeding unit, meaning that the laser beam is creating a mold pool here and the laser beam is close to vertical and the wire is fed into the molten pool created by this laser beam from the side, as you are seeing. This is typically called as the lateral wire feeding method. One can notice that the laser beam is usually, or the laser head is not typically exactly vertical. It is because if there is any back refraction, the laser beam may travel inside the optics and it may damage it. Therefore, to avoid the damage of the optical head, it is slightly tilted on one of the side in such a way that the laser beam getting reflected from the surface of the substrate will go somewhere like this, but not will travel into the optical head. On the other hand, when we use omnidirectional systems, there are three possibilities. One is called as the rotating wire feeder, another is annular beam, and the third is split beam. In the case of rotary wire feeder, the wire feeder is capable of rotating around the melt pool, and it is essential as you want to maintain a particular type of feeding mechanism. The different type of feeding mechanism we shall see in the subsequent slides. The another possibility for omnidirectional laser wire cladding unit could be utilization of the annular beam. When the annular beam is utilized, the laser beam is first getting converted into a hollow beam, as you are seeing here in this diagram. As the laser beam is hollow now, one can feed the wire from the center, and then at the focal point, when the hollow beam will also get converted to solid beam, the wire will also get merged with it, and at that point the melt pool will be created. Such heads are capable of moving in any direction without any issue associated with the geometric and material properties of the deposited bead. This is an example of annular beam. The third possibility could be the split beam. In the case of split beam, the laser beam which is coming from the top passes through a beam shaper and splitter. As a result, the laser beam got splitted into multiple beams, and then later on, utilizing the mirrors, these laser beams are further get converged at a point. The point when the laser beam was getting splitted, the space will be created right in between, and then in that space one can feed the wire, as you are seeing here in this diagram. Now the benefit here is the wire is at the center and it is surrounded completely by the laser beams. Therefore, the process becomes omnidirectional and you can move in any direction. This is a typical system corresponding to the lateral feeding. Here you can see there is an optical head and it creates the laser beam which falls down onto the substrate. And then here there is a wire feeder which is feeding the wire towards the melt pool, and it is coming from the side, and that is why it is popularly called as the lateral feeding. On the other hand, what you are seeing here in this diagram is a rotary wire feeder in which the wire feeder can rotate around the laser head in such a way that the desired deposition direction can be maintained. This is the wire feeder here which is feeding the wire, and it is capable of rotating around this system. Of course, in such cases the system becomes very bulky, and as you can see here as well. Now this video will give you an idea of the lateral feeding based laser metal wire additive manufacturing system. Here it can be observed that the laser beam is coming from this vertical side, and it is creating a melt pool into the substrate or pre-built layer. And then the wire is fed through this tube from the side. The another tube is used to supply the organ in such a way that the melt pool can be protected from the outside gases. This particular slide will explain about the difficulties we usually face corresponding to the lateral wire feeding laser cladding units. So for an instant, consider the case shown here, in which the laser beam or the laser optical head is moving in this direction as shown by this arrow, and the wire is fed from the side like this. The top view of the same can be visualized like this. Here this center part is the melt pool, and this is the deposited bead. This particular type of feeding mechanism is called as front feeding mechanism. In this case, the moving direction is like this, and you are feeding the wire from the front side of it. There are three possibilities where the wire may get melted. The wire may get melted at the leading edge, meaning to say at the very beginning as well. Also, the wire may melt at the center edge after entering into the melt pool in the top view, and the wire may also melt at the trailing edge, which is somewhere here. If the wire is melting at the center edge, then there may not be many issues, but if the wire is melting at the leading edge or the trailing edge, then you can assume and you can visualize that if the deposition direction will change, definitely there will be some issues associated with the deposited bead shape and size. The same can be observed in the case of backfeeding as well. The scenario is shown here in this diagram. Here, this is the laser optical head which is creating the laser beam here, and it is moving in this direction. As it is moving in this direction, the wire is fed from the back side of it, and it is a lateral feeding, of course. In that case, if we observe the top view of the same, it will look something like this. Here, this is the moving direction, and the wire is fed from the back side, and this is called as back feeding mechanism. Similar to the front feeding mechanism, in the case of back feeding mechanism as well, the wire may get melted in the beginning, and then it will be called as the leading edge, wire melting at leading edge. If the wire melts at the center, it will be called as wire melting at the center edge, and if the wire melts at the end, then it will be wire is melting at the trailing edge. Now you assume that the wire is melting at the trailing edge, and we are following the backfeeding condition. Suddenly, due to the deposition direction change when we are depositing on a substrate, the moving direction has become like this, right? Suddenly, instead of going in this direction, we are now going in this direction. Then it will become what? It will become front feeding. Suddenly, from the back feeding, it will change to the front feeding mechanism. And in such case, then the deposition which was happening earlier at the trailing edge will occur to be happening suddenly at the leading edge. Therefore, the mechanical and the metallurgical properties of the deposited beam which you were achieving earlier in the case of backfeeding will definitely change as the feeding mechanism will switch to front feeding. Therefore, it is recommended that to always stick to a particular type of feeding mechanism throughout the process. And that is why the rotary wire feeder is quite popular in the case of the laser metal wire additive manufacturing system. So assume that now if I have a rotary feeder which can rotate the wire feeder like this, then if the deposition direction is changing, then definitely the wire feeder will rotate and bring the wire from this position to the different position, which will look something like this, right? And hence your feeding mechanism will remain consistent, either back feeding or front feeding. Several studies has been done in the literature, and it was found that the front feeding was popularly beneficial, particularly in the case of laser metal wire additive manufacturing system. However, in some cases, particularly for laser cladding system, not additive manufacturing systems, where only one layer is deposited and only the motion was in one direction, backfeeding was also supported by some of the researchers. But my recommendation will be that if you are dealing with the additive manufacturing system, then preferably we should use the front feeding mechanism. The next system is when the laser beam is in the shape of an annular beam. In this case, the wire can be fed at the center and you will be able to move in any direction without having any issue like we discussed in the case of lateral feeding. Here, first of all, as you are seeing, there is a solid beam which travels through a particular type of optical system and getting converted into a hollow or annular or donut shaped beam. The first optical system is an hexagon. Hexagon works like you are seeing here in this diagram. For example, this is the solid laser beam. Assume that there are half of the rays traveling on the top surface and the half of the rays are traveling on the bottom surface. The rays those are striking on the top surface, top slant surface, will get deflected in this direction, and the rays those are getting deflected from this particular surface will get deflected on the bottom side like this. As a result, when the laser beam will again come out in the air from the lens, then again they will become parallel to the original one. So now the beams are parallel to the original one, but they got splitted into two halves. As a result, you will be having a donut shape or annular beam from a solid beam when it passes through the hexagon. After converting a hollow beam, then it passes through a prism. When this type of prism is used, it splits this beam into two halves. So the main purpose is to split. So if there is a solid beam like this, donut shaped beam, where the laser power is available in this zone, which I am highlighting here, in this zone, and when it passes through the prism, it will split it into two halves like this, one here and another here. As a result, now you will be having some space available from where you can enter your wire. So the laser beam going here, first getting converted into an annular shape beam after passing through an hexagon, and then it passes through a prism where the laser beam itself getting splitted. Then it strikes with a mirror which is at 45 degree and it deflected these rays onto the bottom side. At the time when it was getting deflected, we already having some space available, we can insert a wire through this space. Then the next job will be again to bring this splitted beam back to the merged annular beam shape. So an inverted prism will be used then, and hence by utilizing this inverted prism, the splitted beam has further or again getting converted into the annular shape beam as you are seeing here. Further, there is a optical window which protects any fume or any spatter going towards the optics. It protects that, and also there is a sphere used particularly to converge this donut shaped beam to a focal point. Wherever this donut shaped beam is having a focal point, meaning to say the minimal diameter, that is particularly used as a focal point, and the wire is fed into the melt pool created on this point. So this is typically the optical arrangement for an annular beam shape laser metal wire additive manufacturing system. This video will give you an idea how this particular system works. As you can see, the wire is at the center here. This is the wire, and it is depositing material onto a substrate. The laser is in the annular form. Here in the slow motion, the same video is shown here. The laser is not visible, but it is coming in the form of a cone like you are seeing on the left side diagram. It is creating a melt pool, and the wire is getting fed from the center into the melt pool. Now one can appreciate very important thing here. There is nothing like front feeding, back feeding, side feeding here, which we discussed earlier in the case of lateral feeding systems. Here there is always a feeding which is consistent, and the wire is coming from the top. This type of heads are particularly developed by Precitech. Being independent of the direction of motion, this type of system is very much popular for additive manufacturing and can realize the objects without any metallurgical and geometrical issues. The next system is where the laser beam is splitted into 3 beams, and then they got merged at a point and the wire is fed from the center. The head is bit simpler, the one which discussed earlier where the donut shaped beam was used. Here it is an approximation of the same, but instead of having a cone of the laser surrounding the wire, here in this case 3 beams will be there. So the optical arrangement here in this case is not very complicated, and the head becomes much more compact in this particular system. Here the principle is very simple. This is the laser beam coming, which is a solid beam. First it is getting splitted by utilizing the appropriate optics. Once this laser beam gets splitted into 3 laser beam, there are 3 mirrors associated. They further directed these beams to getting merged at a particular point. The portion where the laser beam got splitted and further getting merged, the space got available to feed the wire into it. As a result, the wire can be coming from the center side, from the top, and the laser beams are surrounding the wire from all the sides. So this particular video will show you that how this system works. As in this case, the wire is coming from the center, you can see, and 3 beams are coming from 3 sides. Those are at 120 degrees apart. It can be noticed that the laser beam is not visible because here the laser is used is a diode laser which is having a wavelength of 1000 nanometer, which means it is definitely not into the range of the visible light, and that is why we are not able to see the beam. This type of system is also very popular when the laser is used along with the metal wire to create the parts by utilizing the additive manufacturing technique. It can be noted that this particular system is much more compacted as compared to the system I discussed last time. Here, because the optics is relatively less complicated. And of course, the process is omnidirectional. You can move in any direction. There is no side feeding, front feeding or back feeding type of thing here. This particular head is developed by IWS Fraunhofer. Let us now try to do it on our own. So here we have made a DIY experiment in which you can utilize a laser beam, which is nothing but your laser pointer, and we'll try to split this beam onto the two screens shown here. So for that, we have taken a transparent window, but we know that it is not all the light will get transmitted through that. Some of the portion will get reflected as well. We will utilize that advantage and we'll place this window, which we are calling it as splitting window, in appropriate way such that two spots will be observed, one on the back side screen and another on the right side screen. Here it can be observed, now we have two spots and they are getting generated from the same source. So the laser beam got split into two. Of course, now we can utilize two appropriate mirrors in such a way that these two beams can further getting merged onto the desired location like they typically do in the case of three beam system. Let me put mirror 1 and mirror 2 here, and these two beams, those are getting generated from the same beam, now will get merged at a single spot. Now you can see very clearly now that we have enough space in between available and we can feed anything towards the mold pool or towards the focal point from the empty space. So this is how typically they converted a laser beam into multiple beams and then further merged them towards a particular focal point in order to generate the omnidirectional unit such a way that you feed the wire from the top vertically. So you can also try this experiment on your own. Now let us discuss about different process parameters associated with the laser metal wire additive manufacturing. These process parameters are divided into four categories. The first is the thermal energy. The second is material and design. The third is feeding, and the fourth is motion and path. In the first category, which is corresponding to the thermal energy, the process parameters are like the power of the laser, the beam diameter, beam profile, working distance, and the wavelength. However, if you have already procured a system, then you will not be able to change dynamically the wavelength, the working distance, the beam profile, and diameter of the laser also until you are not changing the optics of the head. Therefore, the only parameter usually which is in control of the user with the consistent or the same optical head without changing any optics is power. And typically, if you want to change the material, the parameter available which is typically controlled to give different energy so that you can melt your wires, different types of wires, the power is typically the process parameter. On the other side, in the material design, the parameters are involved like the material of the wire, the diameter of the wire, the material of the substrate, substrate geometry, and the feature geometry. Here one can notice that the material of wire and the material of the substrate can also be different. They need not to be same. Not only that, in some cases when we create the functionally graded materials, the pre-built layer can be of different layer and then the next layer could be of different layer, material. Like in the case of functionally graded material, the first layer is deposited with one material and then the second layer is deposited with another material. Therefore, the material for substrate and wire keep on changing as per the requirement. In most of the cases, the substrate geometry, until we are not using multi-axis system, the substrate geometry is typically flat and as a result we deposit on a flat surface. But it is very much essential that the process parameters such as the feature geometry and the geometry of the substrate are very important. On the other category, we have the feeding. It can be the feeding direction. As you have seen, if you are feeding the wire from the side, which is popularly called as lateral feeding system, the feeding direction was governing many things. we have seen three different types of feeding mechanism: front feeding, back feeding, and side feeding. So different type of feeding mechanism will give you different metallurgical and geometrical properties. Therefore, it is usually considered as a process parameter. Then the position of the feeding and the angle of the feeding. If you are feeding the wire from the side, at what angle you are feeding it into the melt pool, and at what position it is getting melted into the melt pool. We have seen the three position: the leading edge, at the center, and the trailing edge. Then the next is wire feed rate and gas flow rate. In all these process parameters, typically they are fixed for a particular geometry. We do not change it much while changing the wire or changing some other materials or other ambient conditions. Usually the process parameter which is changed very often, or which is in hand of the user very often, is the wire feed rate. If the wire feed rate is low and high, definitely it is going to affect our process. Now let us discuss about the fourth category, which is motion and path. The first in this is the scanning speed. At what speed you are moving your laser cladding head with respect to the substrate. The next is the track overlap ratio. It is the distance between the two consecutive passes, and you can easily find out this optimal overlap, like we have already discussed it in the case of MIG welding. The same analogy can be extended here as well to find out the optimal overlap. Typically, if the cross section of the bead is parabolic, we know that the optimal overlap is 2/3 of the width of the deposited bead. Then, in what deposition path you are following to deposit the material. There are several deposition paths we have discussed in one of the module for area filling strategies like zigzag, contour parallel, contour offset. We have seen the Hilbert path, fractal base path, and many other paths corresponding to the deposition. The deposition path very much governed nowadays, and it is a very important research area for the residual stresses and the defects generated into the object. An appropriate tool path planning or deposition path planning is essential for such systems. Then the interpass time after depositing one layer or one track, how much time we should wait. And then the preheating temperature, which is also very essential process parameter to reduce the residual stresses or to reduce the defects associated with the process. So what we are seeing here, the three main parameters, like I already mentioned, for a particular part, if the CAPP is already defined, the parameters in the hand of the user are typically the laser power, the wire feed rate, and the scanning speed. Typically, these three parameters are sufficient enough to take care of the deposition quality and to take care of the metallurgical and the geometrical quality of the deposited beads. The other parameters shown here in the green color are also in the hand of users, but they typically do not change much, and for a particular wire they remain same. The other parameters shown here in the yellow color are also in the hand of user, but they also doesn't get changed much once the process is established. Let us now discuss about typical range of these process parameters. Those are important for any laser metal wire additive manufacturing system. Such as the first important process parameter I already mentioned is the laser power. So the first parameter is the type of lasers. Typically, in the case of laser metal wire additive manufacturing, the diode laser, disc laser, NdArc laser, fiber laser is used. However, in few cases, the CO2 laser is also used. Although the CO2 laser is not very efficient when processing the metals. The diode lasers, which are having around the wavelength of 1000 nanometer, are typically more efficient. We know that the CO2 laser is having a wavelength of around 10,000 nanometer, and due to the high wavelength, the CO2 laser is not very efficient in handling or processing the metals. Therefore, the diode laser, disc laser, NDR laser and the fiber lasers are more popular in the laser metal wire additive manufacturing system. However, the power of the laser should be very high, as we are going to create a melt pool at a very local area in a very bulk material or the substrate sometimes. Also, there are issues associated with the reflectivity of the laser. Therefore, a high power is typically required in such system. A typical range of the laser power used in laser metal wire additive manufacturing varies from 1 kilowatt to 20 kilowatt. The deposition rate by which we are depositing the material onto the substrate or pre-built layer typically varies from 1 to 50 gram per minute for laser metal wire additive manufacturing systems. Also, the typical layer thickness we usually achieve in such a system is around 1 mm, or in other words 1000 micrometer. It is very difficult to obtain the layer thickness lesser than this value, but getting higher than this value is quite possible. Wire diameter. Typically, the wire diameter varies from 0.2 to 1.2 mm in such systems. In few systems, it may vary, it may go up to even 2 mm. However, obtaining a wire diameter less than 0.2 will be very difficult, because usually the wire, when it comes out of the spool, is having the curvature of the spool as well, and due to that it may deflect here and there and may not hit the melt pool accurately, and your deposited bead may not be really very accurate. Also, it can be noticed that such systems like laser wire metal additive manufacturing systems are typically used for high deposition rate. Therefore, it is preferable to use the high diameter of the laser. The other parameter is the bead width. It usually varies from 5 to 15 times of the wire diameter. The surface finish we usually achieve by this process on the parts created varies from 40 to 60 micron, though it's not very good surface finish. Therefore, typically in all the parts created by this manufacturing system goes through another system in the end for final finishing if required to achieve the desirable surface roughness. The travel speed or the scanning speed varies from 500 to 2400 mm per minute in these systems. It can also be noted that the laser metal wire additive manufacturing systems are not only popularly used for additive manufacturing, but the same system can be utilized for cladding, for the surface protection, for surface treatment, as well as for repairing and the feature addition on the damaged parts. Now let us discuss a little bit about the wire deposition characteristics. Like I have already mentioned, typically three parameters, the laser power, the scanning speed and the wire feed, governs the wire deposition characteristics. And these are the three parameters usually are in the hand of the user to change very quickly. These wire deposition characteristics could be, as the first is wire dripping or the droplet transfer. The droplet transfer occurs when the available energy is too high, and which melts the wire tip much before when the wire is about to reach the melt pool. So before even the wire reaches the melt pool, it gets melted and the metal is transferred in the form of droplets. It is usually observed when the wire feed is excessively low. You are going very slow. You are feeding the wire very slowly into the melt pool. And if that is the case, it will absorb, the wire will absorb lot of energy from the energy beam itself, and it will get melted much before the melt pool. Due to that, sometimes the discontinuous tracks are obtained, as you are seeing here in this diagram. So whenever you use the laser metal wire additive manufacturing system and obtaining this type of bead, you can easily predict that your wire feed speed is too low and you may further increase it. The other possibility of the wire transfer could be the smooth wire transfer. This is the most desirable transfer condition. It is observed when the available energy is sufficient enough to melt the wire tip at the point or close to the point of intersection with the melt pool, as you are seeing in this diagram. Sometimes, as in this case, the wire is getting melted very close to the melt pool, the droplet form at the tip of the wire just get merged with the melt pool and form a bridge of the molten material. And that is why sometimes it is also called as bridge transfer. This is the most stable mode of the metal transfer in the case. Here the deposited bead will look something as you are seeing on this diagram, and they will be very smooth without any defect like you have seen in the earlier stage. However, it may also possible that the wire feed you have increased with so high value that it is not able to absorb enough energy from the laser beam, so in such a way that the tip getting melting close to the melt pool, instead it is getting plunged into the melt pool. In this case, the available energy is low and hence the wire entered the melt pool in a nearly solid form, resulting in a collision of the wire tip with the solid substrate at the base of the melt pool. A collision with the substrate caused the wire tip to move away from the center of the melt pool, and hence in this case the wire eventually melted by the energy of the melt pool, not completely by the energy available with the beam. It usually occurred, like I already mentioned, due to the excessive feed rate of the wire. As you are seeing here in this diagram, these are typical deposited beads due to the excessive feed rate of the wire. Here you can observe that the wire is getting plunged, and due to the plunging it is creating this type of serrations into the deposited weld bead. Somewhere the weld bead is thicker, somewhere it is thinner, and it is discontinuous as well, and it is not following the center line of the path. This is mainly because of the hitting of the wire in the solid form into the melt pool. This particular phenomena is called as wire stubbing. So how do we find out the optimal process parameters, particularly the laser power, the wire feed rate and the scanning speed, in such a way that your wire always gives you, or wire always transferred into the melt pool through the bridge transformation or the smooth transformation? In such case, two parameters are typically defined by the researchers. The first is called as energy per unit length of the track, which is written here as EL. It is the measurement in joule per mm, and it is combined by the laser power and the traverse speed Vt, the speed of the laser beam onto the substrate. As you know that the power is in the watt, which is often written as joule per second, and the velocity of the laser head is typically given as in the mm per second. As a result, this parameter which we are defining here, energy per unit length of track, EL, is having unit joule per mm. The another parameter is VL, which is nothing but the deposition volume per unit length of the track pass, and it is defined in mm cube per mm. It is defined as the area of the wire which we are feeding into the melt pool into the wire feed rate. That is why this particular equation, A into V omega or VW, this particular equation A into VW is giving us the volume deposition rate or the volume flow rate. Let me write it as mm cube per second. Similarly, on the bottom side, the travel speed is given, and we know the unit of the traverse speed will be mm per second. That is why this ratio is coming to be as mm cube per mm, and it is nothing but the volume deposited per unit length of the track. So we have two parameters. We know the energy available per unit length of the track, and we also know the volume deposited per unit length of the track. Now we have to just find out the optimal range of these two parameters, EL and VL, and we can map the entire process parameters in such a way that you obtain the desirable metal transfer, which is of course the bridge transformation or the smooth transformation. So whenever you are going to deal with a new material, the task is to first make the process map of that particular material. So this is a typical process map for Inconel 625 wire of diameter 1.2. Here you can see that the results obtained corresponding to the different values of the parameter which is decide the energy available per unit length of the track and the volume deposited per unit length of the track, EL and VL, are plotted together. Now here, after plotting the different combination of EL and VL, the process map is defined, which is clearly showing the zone 1, which is corresponding to the zone. If we select any parameter here in this zone, will give us the dripping or drop transfer. The zone 2, which is very narrow and very uncertain, you may get the dripping, means the droplet transfer, or may not also. Then the next is the third zone where the smooth transfer of the material is occurring, and then the zone 4 where the smooth transfer may occur or may not also. Then the fifth zone where the stubbing will occur. It is only possible to plot this type of process maps after performing certain number of experiments. Like these red dots what you are seeing here are correspondingly when the traverse speed is 1.7 mm per second. Now if the traverse speed is given to us, then this Vt will be nothing but 1.7, and here also Vt will be 1.7. Then to vary the EL and VL, we need to vary only power and the wire feed rate. The range of the wire feed rate is also given, and the range of power is also given. Correspondingly, we will obtain the value of EL and VL, and we will make the appropriate dots. And we will observe the wire, and we will observe the deposited track visually, and if it is found to be drip transfer, we will make a mark that this is the drip transfer, and if it is smooth transfer, we will make it marked as smooth transfer. Like this, if we plot each and every data corresponding to the range, like this blue colored triangle data is correspondingly when value of Vt is 3.3 mm per second, and then this cross mark is correspondingly when the traverse speed is 5 mm per second. It can be seen that as the traverse speed is keep increasing, the zone, which is the zone corresponding to the smooth deposition, keeps on reducing, right? Here it is a larger zone, while we are coming down, this zone is keeps on reducing. It is happening because we are increasing the speed of the optical head or the laser head. As the speed is increasing, of course the energy available per unit length of the track will be less, and hence you will not be able to transfer your wire or deposit the wire appropriately, and hence the smooth transformation may not occur. This type of process maps, like I already mentioned, are very essential whenever you are switching from one wire to another wire. You need to just plot it, and whenever you are going to use a new process parameter, check it in which zone it is falling, so that you can predict whether you are going to get a smooth transfer, a drip transfer, or the stubbing transfer of the material into the substrate. Now let me tell you that how we can find out the critical power associated or required for depositing the material. It is a very straightforward calculation, but may help you to obtain the value of the required power. Therefore, to obtain the critical power, one can use very simple heat balance equation. Here in this, I am writing it as eta P naught, where eta is the efficiency of the laser, because all the laser which is falling onto the substrate does not get absorbed by the material. Some of the power got reflected also. If that is the efficiency, then this much power is available onto the substrate from the source. Then there will be power consumed first by the wire which is getting melted, right? And there will be power consumed by the substrate as well. So in the case of wire, definitely it will include the wire feed rate. Therefore, if the wire feed rate is defined as by Vf here and the diameter of the wire is dW, then this is the volume feed rate of the wire towards the melt pool. Then rho is the density of the wire, then into Cp Tm minus T naught, where Tm is the melting point of the wire and T naught is the temperature, initial temperature, which is considered to be at room temperature of the wire, plus latent heat required for melting. So like this, we can find out the energy required to melt the wire. At the same time, we have to melt the substrate as well, so that we can obtain appropriate penetration into the substrate. Otherwise, the droplet will be just on the deposited on the substrate without having any metallurgical bonding with the substrate. Assume that dP amount of the material getting penetrated or diluted into the substrate. So dP is the depth of the penetration, while ds is the diameter of the laser spot on top of the substrate. So if I draw the top view, it will look something like that. If this is the substrate, this is the laser beam spot. The diameter of this spot is given by ds, and if I see the side view now, an amount of dP is getting penetrated, right? This is the penetration depth dP. Once I have ds and dP with me, now I can find out the energy required. If that laser head is traveling with a speed of, for example, Vd, that is the deposition velocity onto the substrate, then I can easily find out the energy required to melt this much portion of the substrate, and it will be pi by 4 ds into dP into Vd, velocity of the laser head, into rho. Rho is the material of the substrate, and if the wire and substrate are of the same material, then rho can be same. Then Cp is the specific heat, Tm is the melting temperature of the substrate, and T0 is the room temperature, and L is the latent heat of melting. So this much power will be required to melt the substrate. Please note that we have not considered any losses here. There will be definitely some conduction loss, some radiation loss, some convection loss as well. Those should be accounted, but just to find out the minimum power required, this formula will work. So the typical process parameters I am considering for a process and trying to find out how much power is required. If I am using a wire of diameter 1.2 with wire feed rate of 25 mm per second and with the deposition rate or the deposition scanning velocity of 25 mm per second, if we require the penetration depth of 0.5 mm, density of the material is 8000 kg per meter cube, the specific heat is 460 joule per kg degree centigrade, melting point of the material is 1800 Kelvin, the initial temperature of the wire and the substrate is 300 Kelvin, latent heat of melting is 2.7 into 10 to the power 5 joule per kg, efficiency is 70%, and hence by utilizing this formula we can find out the minimum power required for this deposition process, and it is coming to be around 712 watt. In a similar fashion, you can also find out the critical power required for the given process parameter. But please note once again, we have not considered the conduction, we have not considered the convection or radiation. Those should be accounted appropriately. And also the efficiency of the laser, it will highly depend on the material, and it also keeps on changing with the temperature. So those should be accounted appropriately to find out the exact value of the power required. But this will give you some idea that how much minimum power of the laser will be required. So with this, we have completed the discussion on the laser wire additive manufacturing system. Thank you very much.